Today we're going to discuss the atomic spectra, the Bohr model of the atom, and then the quantum mechanical model. So the atomic spectra is when atoms absorb energy. So let me get your fill-ins here. So high-ray, emitted, and rainbow. What we know about this atomic spectra is when atoms absorb energy, electrons move to what we call the higher state. So as they absorb energy, they jump up. So they jump up to higher energy levels, like from energy level 1 to energy level 2 to energy level 3. But again, we know these electrons that go up must also then fall back down to ground state. And as they fall back down to ground state, they actually will emit this energy. As they emit the energy, this is how it's important now. The distance in which they fall dictates the amount of energy released. The amount of energy released dictates the color of light we see. In our visible spectrum, we have down here, up here we have the violet. The violet is our highest energy of light. And then down here, the lowest energy of color of light we have is red. So just above us, we have the ultraviolet, and just below us, we have infrared. So everything that falls right in that area is our visible spectrum. Now we use the visible spectrum to identify different elements as well. The continuous white light, we're going to see the continual spectrum of colors. We see the rainbow of colors. What's unique though about these electrons, we know electrons are orbiting around the nucleus. What's unique about this is that every element gives off specific bands of light. So their electrons jump up, there's same electrons jumping up, and there's same electrons falling down. And they do the same distance. They absorb the same energy going up, and they release the same energy going down. Therefore, they release the same bands of light every single time. When we saw this with the diffraction gradients, showed us that only specific bands of light are given off. Our eyes do not see these bands of light. We actually blend them together and we see only one color. And so we took a look at this, and this is what we call the atomic line spectrum. The atomic line spectrum. These are specific bands of light given off by elements. And we saw a list of different elements here and their specific bands given off. And these bars actually acts like a barcode, and that if we could actually scan it, it would identify the same element every single time. So an explanation of this atomic spectra. In the Bohr model, the lone electron, the hydrogen atom, can have only certain specific energies. And so for hydrogen, again, the Bohr model could explain hydrogen. So we know this when electrons are in lowest possible energy, we call that their ground state. Good term to know, so we call it their ground state. When they are hit with energy and they absorb the energy, they jump up to a higher energy level, which is called the excited state. The amount of energy they absorb is quantized or bundled up, so we call it a quantum of energy. A quantum of energy is energy formed. When it absorbs that quantum energy, the same quantum of energy absorbed, the same quantum of energy released. When we call it that quantum of energy released, we're talking about a photon or a bundle of energy release. The light emitted by an electron moving from a higher energy to a lower level has a frequency directly proportional to the energy change of the electron. We know that their frequency and energy are directly related. So the Bohr model saw these electrons going up, but what goes up must come back down. And we saw that. So remember, we can go all the way up to energy level 7 in this situation. But it goes up as it goes up in these energy levels, it again absorbed energy going up. So it starts at ground state, it hits with energy, it jumps up, and then what goes up must go back down. As it drops back down, it's actually releasing this energy, or this photon of energy or bundle of energy. Now, once again, the distance in which it falls dictates the energy release. The energy release dictates the color of light we see. For hydrogen, we actually had 4 bands of light actually given that we actually see. There are some up in ultraviolet, and there are also some in infrared, but these are the 4 bands that fall within our visible spectrum that we actually see. We do know these, again, spectrums, what we saw here about these energy levels, these energy levels are equally spaced. We know that's not true. They are not linearly spaced. We know that as we go out, the actual energy levels really get closer and closer and closer together. We see that actually in this one. Again, another example, another picture of this. Here's our Bohr model. We go all the way up to energy level 7. Where these energy levels get closer and closer together. That's why we saw overlapping, right? Remember, that's why we saw the 4s2, and then we saw the 3d, and then we saw the 4p. We had that overlapping occurred there. And the reason why the overlapping is because these energy levels get closer and closer together as we move out and increase in energy. As we drop back down, these are the 4 bands of light that we actually see for hydrogen. We jumped over this, but I'd like you to pay attention to it. There are 4 scientists behind this. This is hydrogen only. We're talking about here, hydrogen only. So the element is hydrogen, and hydrogen gives off these, this is all light given up by hydrogen. Lyman series, the scientist Lyman, all of these colors were UV. They're all in ultraviolet. It's in the Balmer series that we have our four bands of light that we actually see all fall within the Balmer series. One of them in the Balmer series is ultraviolet. The Paschen series, everything drops back down to energy level 3 is Paschen. These are all IR, they're infrared. And the bracket falls back to 4, and they are also all infrared. So they fall below our lowest energy light, which is red. Ultraviolet is above our highest energy light, which is violet. So these, again, are the scientists behind it. Beware of these scientists, especially the Balmer series. That's the series in which we see these 4 bands of light. So again, we know every element gives off specific bands of light. This is helium again, and the key thing is it's so consistent, it acts like a fingerprint, just like our fingerprint could identify us. And our fingerprint is unique to us as well. So quantum mechanics, Albert Einstein, he successfully explained the experimental proposition that light could be described as a quantum of energy. So there's this bundle of energy or a particle, and this quantum of energy was called a photon. So again, the bundle of energy given off, the quantum of energy given off is called a photon. De Broglie developed an equation that predicted the moving of objects in a wave-like behavior. So this is where we understand that light is both a particle and a wave. A particle and a wave. And that's where we dealt with this situation. So no de Broglie, wavelength, and Einstein. Today's wave-like property, beams and electrons, are useful in magnifying objects. We can use what we call electron microscope. It shoots electrons. The electrons return actually helps us, since electrons are so small, it helps us see details in a very small object. And this is actually a mite. So very, very small, and we actually see the fine details on this insect. The Heisenberg uncertainty principle, very important to know. Heisenberg uncertainty principle just knows it's impossible to know the, again, its exact velocity and position of an electron at any given time. The more we know about its velocity, the less we know about its position, or vice versa. So the more we know about one, the less we know about the other, or vice versa. So we can't know both of them at the same time. And that was the Heisenberg uncertainty principle.